Thermal expansion. Most materials expand as their temperature increases and contract as their temperature decreases. This is notably true of metals. Material objects are three-dimensional and expansion is in 3 dimensions, but we start by looking at expansion in 1 dimension, which we call linear expansion. In many cases, we are only interested in the expansion or contraction in 1 dimension, for example, the length of a rod. Here is a rod of initial length L0. If its temperature increases by an amount delta T, then its length increases by an amount delta L. In practice, delta L is very small, but it is drawn bigger here so that it can be seen. Now delta L equals alpha L0 delta T. This is the formula for linear expansion, and alpha is the coefficient of linear expansion for the particular material that the rod is made of, with unit Kelvin to the -1 or degrees centigrade to the -1. We can see this from the formula rearranged to give alpha as a function of the other quantities. This formula is only approximately true, but it is a good approximation for relatively small delta L. The formula can be written in a different way as the final length L after the change, by first noting that L equals L0 plus delta L, and then writing L equals L0 into 1 plus alpha delta T. This also applies to contraction, which occurs if the temperature decreases, so the formula applies to both expansion and contraction, hence generally to a change in length due to a change in temperature. Here are some examples of alpha for 3 common metals. Notice that alpha is very small, of the order of 1,000th of a percent per degree. We can use linear expansion to determine how an area expands or contracts. Consider a rectangular plate with initial lengths x0 and y0, and initial area A0 equals x0, y0. The plate expands linearly in each of its 2 dimensions by delta x and delta y, and the area increases by delta A. The additional area contains 3 rectangles of areas x0 delta y, y0 delta x, and a small area delta x delta y. For delta x and delta y small, delta x delta y is very small in comparison to the 2 larger areas and may be neglected. So the increase in area is approximately delta A equals x0 delta y plus y0 delta x. Algebraically, delta A is equal to A minus A0, which is equal to x0 plus delta x times y0 plus delta y minus x0 y0. Then expanding equals x0 y0 plus x0 delta y plus y0 delta x plus delta x delta y minus x0 y0. The x0 y0 cancel, and we neglect delta x delta y to get delta A equals x0 delta y plus y0 delta x as we saw graphically. We can rewrite this as delta A equals x0 y0 times delta x over x0 plus delta y over y0. Now expansion in each dimension obeys the formula for linear expansion. So delta x equals alpha x0 delta t, and delta y equals alpha y0 delta t. So delta x over x0 equals alpha delta t, and also delta y over y0 equals alpha delta t, and we can write delta A equals A0, which is the x0 y0, times alpha delta t plus alpha delta t twice, which is equal to A0 times 2 alpha delta t. We see that the coefficient of area expansion, which does not have a dedicated symbol, is 2 alpha, where alpha is the coefficient of linear expansion. Note that area expansion applies not only to the special case of a rectangular plate, but to any area of any shape. We can follow the same process for volume expansion. This time, for simplicity, consider a cube of side L0 that expands by delta L in each of 3 dimensions. In this case, we use calculus to find the infinitesimal increase in volume. The volume of the cube is V equals L cubed, and then dV equals 3L squared dL. Since delta V is small, we can then approximate it as delta V equals 3L naught squared delta L. Again, the linear expansion is given by delta L equals L naught alpha delta T. So delta V equals L naught cubed times 3 alpha times delta T. And we can write delta V equals 3 alpha times V naught delta T, or delta V equals beta V naught delta T, where beta, which is equal to 3 alpha, is the coefficient of volume expansion. As with linear and area expansion, the final volume may be expressed as a factor times the initial volume. Now let's look at two examples from the textbook. First, example 17.2. A steel measuring tape has an initial length L0 equals 50.000 meters at an initial temperature of 20 degrees centigrade. There are 3 decimal places, 0.000 meters, because the change is going to be small. Part A. Find the new length L for T equals 35 degrees centigrade. So the tape expands to a greater length because of the increase in temperature by 15 degrees centigrade. That's delta T. So we use the formula L equals L naught times 1 plus alpha delta T. So putting in the numbers, we find that the new length of the tape is 50.009 meters. So the change in length, delta L, is 9 millimeters. It's a small change, but nevertheless a change of about 1 centimeter due to the 15-degree temperature increase. Part B. At 35 degrees centigrade, the tape measures a length of 35.794 meters. At 20 degrees centigrade, the tape is accurate. So 1 meter on the tape will measure 1 actual meter. But when the tape expands, 1 meter on the tape is going to measure a longer distance than 1 meter. So 1 meter on the tape is actually 1 plus alpha delta T meters. Therefore, the actual length that has been measured, LA, is equal to 1 plus alpha delta T times the measured length, LM, which is the 35.794 meters. And so the actual length that has been measured is 35.8 meters. Example 17.3 is about volume expansion. A 200 centimeter cube glass flask is filled with mercury at 20 degrees centigrade. The temperature is then raised to 100 degrees centigrade. How much mercury overflows? And we are given the coefficient of linear expansion of the glass and the coefficient of volume expansion of the mercury, beta Hg. Both the mercury and the glass flask have the same initial volume V0, and they both expand. But what happens is that the mercury expands by more than the glass, so some of it overflows. Now we're not given the coefficient of volume expansion of the glass, so we need to use beta glass, the volume expansion coefficient, equals 3 alpha glass. Now let's compare the increase in volume of the two objects. Now the flask's volume increases by an amount delta V glass equals V0 times 3 alpha glass delta T. Note that as the glass flask increases in volume, the volume contained inside the glass increases. The mercury's volume increases by an amount delta VHG equals V0 times beta Hg times delta T. The overflow then is the increase in the mercury volume minus the increase in the glass flask volume, which is delta VHG minus delta V glass, which is equal to V0 delta T, because that's a common factor, times beta Hg minus 3 alpha glass. And putting in the numbers, we see that the volume of mercury that overflows is 2.7 cubic centimeters.